Well, I noticed that the videos are probably a little dry, so my effort to punch them up a little bit. Got a joke to start us off. Did you hear about the guy at the furniture factory that fell into the upholstery machine? Well, it was scary, but he's fully recovered now. Ha! Got him. Back to business. Section 1.5 deals with another aspect of functions, that is the inverse of functions. And you may have learned some of this in Algebra 2. Two functions are inverses of each other if f composed with g is equal to g composed with f, and they both equal x. They both simplify and get x. Right? So you can tell graphically if two functions are inverses, or if xy is on, or ab is on the graph of one relation, then reverse those. Y becomes x and x becomes y in the inverse of that relation. So we just reverse the order of the x and y, and you'll have, and it will fall on the inverse of the given function. And further, when looking at the graph, what you'll see if f and g are inverses is that the two graphs will reflect not y-axis reflection, not x-axis reflection, or origin reflection. They would reflect along the line y equals x. And we'll take a look at an example. In this picture, the red graph that you see here is the squaring function. You recognize the parabola. And the blue graph is the square root function. Now, we have to limit the domain of the squaring function to just the positive numbers, 0 and the positive numbers. So if I slide this over here and just take off the negative domain and look at the positive domain, we see that the red graph and the blue graph are reflected about. The green line here is the line y equal x, the identity graph. But all of the points, let's pick some points on the blue graph, excuse me, on the red graph. We know that 1, 1 is on the squaring function, and if you reverse the order, 1, 1, it falls on the square root function as well. The square root of 1 is 1. So that point is on both graphs. Take another point that we know on the squaring function. Let me pan out a little bit. How about 2 comma 4 right here? That's on the squaring function. If I reverse those, then 4 comma 2 would be on the inverse, the square root function. And then continuing on, I mean, if we want to see another example, maybe we say that 3 comma 9, that would be right there, very close to right there, 3 comma 9, then 9 comma 3. 9 comma 3 would be on the square root function, etc. And so, graphically speaking, inverses are reflected about the line y equal x. Now, in order to have an inverse, the function must be 1 to 1. Always restrict the domain. Now, 1 to 1 functions pass the horizontal line test. Every element of the range is paired with only one element of the domain. And we can see that from the squaring function, let me go back to that image. The squaring function, look at y equal x squared, the red graph. It is not 1 to 1 because every element of the range is paired with two elements of the domain. Take, for example, 2. Well, 2 is paired with, well, square root 2. Let's take 4. 4 is paired with negative 2 and positive 2 from the domain. So it is not 1 to 1, and graphically speaking, it would fail the horizontal line test. The horizontal line would intersect the squaring function in 2 places. Now, when I've restricted the domain, we just talked about the squaring function and the domain with the positive numbers plus 0. Then we get just half of the parabola, and it does pass the horizontal line test, and we can talk about its inverse. So again, for the notes, a one-to-one function means that every element of the range is paired with exactly one element of the domain. Remember, that's the exact opposite of what it takes to be a function. A function has to be one-to-one, elements of the domain paired with exactly one element of the range to be a function, and then it's one-to-one when we reverse that. Let's take a look at an example. Let's take f of x equals sine of x. Is this function, could the sine of x have an inverse? In other words, is it one-to-one? Well, I hope that you answered that yes, the sine of x is a function. It's one of the 12 basic functions we learned. But it is not one-to-one because it does not pass the horizontal line test. You try another example. Try the cubing function. Is the cubing function a function? Well, I guess it is. I just said it is. But is it one-to-one? Well, by now you know that the cubing function increases throughout its domain, and so we do not need to restrict the domain, and it does pass the horizontal line test. So the cubing function is one-to-one, and it does have an inverse. Now let's try to take a look at some functions that are not from our 12 basic ones. Try to verify whether f and g are inverse functions of each other. Now remember, algebraically what we're going to attempt to do is to establish whether f composed with g is equal to g composed with f, and they're both simplified to simply x. So let's compute f composed with g. Okay. We're going to take g, and plug in wherever we see x in f. So it's going to say 2x plus 3 over x minus 1 plus 3 over 2x plus 3 over x minus 2, over x minus 1 minus 2. And to simplify that, it's kind of a mess right now with so many fractions in it. Let's get the numerator expressed over a common denominator. And then we'll do the same thing for the denominator. Express it over a single denominator. So in the numerator, the denominator will be x minus 1. 2x plus 3 is just fine. But to get the second term over the denominator, we have to multiply by x minus 1. And I'm going to distribute, so it's going to be times x minus 1 over x minus 1. We're going to distribute that 3 and get 3x minus 3. Down in the denominator, we'll do the same thing. Okay. We're over x minus 1. And 2x plus 3 is just fine. And we have to get this negative 2 or minus 2 over a common denominator, x minus 1. So multiply by x minus 1 over x minus 1. And we get negative 2x plus 2 over x minus 1. I cleaned up the screen just a little bit, but that's the last, that's where we just left off. Let me, combine some like terms in the numerator. We got a 2x and a 3x for a total of 5x. And a 3 minus 3, hey, that's 0 over x minus 1. And in the denominator, it looks like there's a, let's see, 2x minus 2x, they're gone. And 3 plus 2 is 5 over x minus 1. And lastly, this is a division of fractions. So we multiply by the reciprocal. 5x over x minus 1 times the reciprocal of that denominator, which is x minus 1 over 5. This is times. And we can see that the binomial x minus 1 cancels the binomial x minus 1. And this 5 cancels this 5. And all that's left standing is x over 1, which is x. So f composed with g does simplify to simply x. Next, we'll check g composed with f. We'll take this expression right here and plug it in for x here and here and simplify. See if we get the same thing. That numerator is going to read 2 times x plus 3 over x minus 2. 3 plus 3 over simply x plus 3 over x minus 2 minus 1. We plug in f where we saw x and g, and to simplify, we'll probably do about the same thing. Write the numerator over a common denominator. First we have to distribute this 2. That'll be 2x plus 6. And then we'd have to multiply the 3 times x minus 2 over x minus 2 to get that common denominator at 2. Alright. So I'm going to distribute. That's going to be 3x minus 6 plus 3x minus 6. And that is all over x minus 2. Now let's work on that denominator. Again, x minus 2 is going to be the common denominator. And we have x plus 3. It's fine just the way it is. We have to multiply 1 times, or negative 1 times x minus 2 over x minus 2 to get the common denominator. That's going to be distributing that negative 1 with the negative x plus 2. And if I got space here a little bit, we can combine some like terms and simplify this. 2x and 3x is 5x, and plus 6 and negative 6 cancel each other. So we have 5x over x minus 2. 5x over x minus 2 divided by, and in the denominator, combining like terms, we've got x and negative x cancel each other. 3 and 2 is 5. 5 over x minus 2. Looks like it's going to shake out about like the last one. Division is multiplication. Division with fractions is multiplication. So we'll say 5x over x minus 2 times x minus 2 over 5. And it looks like the same game. Binomial x minus 2 in the numerator cancels the binomial in the denominator. The 5 in the denominator cancels the 5 in the numerator. And all that's left standing is x over 1. So g composed with f also produced x. So we can say that, right to the top, these two functions, f and g, are indeed inverses. We've proven it algebraically. Okay, let's see if you learned anything. Take a moment, some paper, and verify whether f and g are inverses of each other. Well, here's the work I put together. F composed with g is in purple. We plug in the function g in where we see x in f. And when we square or square root, we just get the radicand. And 5 minus 5 is 0. We have 2x over 2, which simplifies to x. In blue is g composed with f over here. So I take the square root of 2 times all of f. Plug in f in this parentheses. The division and multiplication by 2 cancel. I have x squared minus 5 plus 5. Negative 5 and plus 5 cancel, so it's the square root of x squared, which is x, and they're equal. So these two functions, g and f, are inverses. We're going over verifying whether two given functions are inverses. Did two examples like that. What if we want to find the inverse of a function, of a given function? Well, it's related to the fact that if a and b are an ordered pair on the function, then b comma a would be an ordered pair on its inverse. So let's see. If f of x is 2x plus 5, find the inverse of x. And take a look at how that notation is. This is not the reciprocal. This is the inverse of the function f. Well, first of all, change the function notation to y equal. So replace f of x with y. And then switch x and y. So instead of y equal 2x plus 5, we write x equal 2y plus 5. And then solve for y. Y equal x minus 5 divided by 2. Put it back in f of x notation. And we have the inverse of f is x minus 5 divided by 2. Let's find the inverse of f. If f of x is the square root of x plus 2. We would change the x's and y's. This would be y equal the square root of x plus 2. And reverse the x's and y's, we get x equal the square root of y plus 2. If I square both sides, I get x squared is equal to y plus 2. And isolating the y, we get x squared minus 2 is equal to y. So the inverse of f is x squared minus 2. But that's a parabola. It's not going to be one-to-one. So let's recall the domain of f would be from negative 2 to infinity. And this is the domain of f. And since the domain of f becomes the range of its function, we switch in the x's and y's. The range of the inverse is from negative 2 to infinity. These are the outputs. So what is the smallest number that x can be to produce a range value of negative 2? Well, if x were 0 in inverse of x, if this is a 0, then the output would be negative 2. So the domain of the inverse would be 0 to infinity. And that's it for today. I'll see you in class tomorrow with the exercises. Don't forget that poor fellow in the upholstery factory is fully recovered. So happy to hear that.